Good morning. This is Dr. Eidelberg, and this presentation will cover process control. We are in Module 10, and we will come into the reference material and click on Lecture 9. The topics which we will cover in this presentation are shown in this slide. They include overview of factory process automation control, some definitions related to PLC. We'll take a look how PLC software programming is being done, including ladder diagram, and then an example of typical robotic application which is being controlled with a PLC. A PLC can be viewed in analogy to an orchestra, and that is the task of the conductor to orchestrate the process of the entire team in order to synchronize their performance, and the outcome will be a beautiful symphony. So we see it in this diagram as the focus of our discussion, which is the PLC, the Programmable Logic Controller, which orchestrates the process of the automated equipment which are grouped together to manufacture parts, and then the robot, which is shown over here, controlled by a robot motion controller, which is a different topic of our lectures, is basically one element of this entire orchestra. Here we see one robot, we see another robot, a third robot, working together with other conveyors and indexing tables and hoppers and various pallets, and the PLC is the one in charge of communicating to the peripheral equipment and receiving feedback information from the various sensors in the peripheral environment, and also controlling in turn the robots. And the human operator or the programmer or the maintenance personnel can communicate with the PLC through their own devices like a laptop, teaching pendant, and then the PLC in turn is being commanded by hierarchical control, which is connected to the other controller in the process. The advancement in PLC utilization are shown as this chart. These charts are taken from the open literature on the internet, and we see over here that 2011 is shown in light green, dark green is 2016. So in 5 years you see that the PLC application, which indicates a lot of automation addition to manufacturing processes, almost 50% in food and beverage, over 30% in machine tool, in material handling processes, pick and place, packaging machinery, paper industry, printing machinery, and also in robotics. It's getting more and more in advance, almost 50% we see over here, with a trend in automation of robotics, that the PLC is becoming many times part of the motion controller, like we have with the Scobot in our lab. And then other industry like plastics, machinery, semiconductor, textile, they all show an increased utilization of PLCs. The basic process that PLC is being programmed is a traditional ladder logic diagram, and we see this resembles a ladder with its rungs. We may imagine the left-hand side is high potential, live. The right-hand side is neutral, we have sensing devices which have to be either on or off that the PLC detects, and then we have output devices that have to be actuated once the line of connectivity from high to low to neutral is closed. So for example, in this case, the coolant button has to be closed, the safety guard has to be closed, and then the line is continuous and relay 1 will work. Alternatively, if relay Y is working and this line is closed, then and also the guard is closed and the push button may be open, and it is still going to conduct the process, and relay 1 will be open. When relay 1 is open, then 1, 2 is going to be closed, and then 1, 3 is going to be closed, 1, 1 is going to be closed. When 1, 2 is closed, then the coolant pump is going to be on. Once the coolant pump is on, then PLC coming into this rung, and then if the machine on button is closed and relay 1, 3 is closed, when relay 1 is open, then relay 2 will open. When relay 2 is going to be actuated, when relay 2 is actuated, then this switch is going to be closed, this switch is going to be closed, and then the contactor of the motor, and so on and so forth. We'll see more of that. The basic configuration of a PLC includes a controller with its output and input units, and interface to the operator, and this PLC is receiving signals which present the status of the process that is being controlled, and then in turn the PLC commands actuators which change the status of the process as needed. The cycle time as the PLC goes through all the rung is shown over here. There is a reading phase of the input, executing the program, diagnostic of the communication, making sure that everything is on par, and then uploading the output and coming back to the first rung. The way PLC has been constructed in industry is typically in several modules. We have the power modules, CPU module, relays which receive command from the output and connect to the equipment actuators, input devices that receive feedback from the sensors, then communication to the user interface, and then the Ethernet to orchestrate the process. It is specified here that the parts include the power supply, the CPU, and the software section over here within the CPU, and then the I/O elements. The typical definitions related to PLC is analog to digital converters, which transform analog into a digital word. Address is a number location within the PLC, and then the analog input or analog output could be part of the PLC process, not necessarily just binary codes. The baud rate is the number of bits per second that can be handled. The BDC is a binary coded decimal that sometimes being communicated. So if there is a need to communicate a value of 2709, then the PLC may be using BCD in order to use binary code in order to describe this element, and the processing way it works, this 9 is being generated by taking 1 times 2 to the 0 plus 0 times 2 to the 1 plus 0 times 2 to the 2 plus 1 times 2 to the third, and 2 to the third is 8, and this is 1 times 2 to the 0 is 1, and then we have the sum of all is 9. Then bits is either 0 and 1, and byte is 8 bits. The power supply converts a line voltage, 100 or 200 volts AC, into what is being used by the PLC, which is 24, typically 24 volts DC output. We see over here that the CPU includes a case plus the PC board. And by the way, all of these information that we are showing over here are pretty much copied and pasted from these references. We thank the contributors for these references, and we encourage the students to click on them and take a look at it in more details, as well as reading in a PowerPoint presentation some of the details which are not covering. Input modules are the modules that interface between the sensors and the PLC, and they may be of various forms. They can provide input through of thermocouples, they can provide positioning input, they can provide PID information for the controllers, and they are a part of the PLC modules. In a more complicated software, we see that there may be several inputs which have to be in series connected. All of these must be connected together in order to close this rung, and these two have to be open in order to allow output 19 to run. Alternatively, if these two guys are open and not closed, but these two are open, then this will also be a parallel path that can allow the system. We see that over here we have the time that a certain output has to be on, and we see that also how it's being described in a chart. The PLC hardware is a mirror image of the software. Once the programmer puts a ladder diagram with all the connectivity, then the hardware engineer or technician will actually make sure that all the power is connected as described to the relays. All the input and all the output are also connected, and you see how they're nicely organized in this particular example. Over here, when we are working on a project with mechanical engineers and electrical engineers, many times the electrical engineer will present the electrical diagrams as shown over here of the connectivity of the PLC and all its peripheral equipment, and that may be one out of perhaps 50 some pages that describe the electrical connectivity of the process. We see here once again that the system of the PLC includes the central processing unit, the memory for program, and also data, power supply, user interface, input modules for sensing devices, output modules for actuators. And then the software is not necessarily the original traditional relay ladder logic, RLL. There are also standards, as shown over here, of advanced programming languages that could be used when programming state-of-the-art PLCs today. Then we see once again that the ladder diagram is resembling the actual ladder with its two sides, positive, negative, and the rungs which connect them. The bits on a certain input or output could be described over here in a so-called drums, and this is showing here 6 bits, and it indicates the timing of each one of them. So on the first 9 seconds, bit A will be on, Then from 9 to 15 seconds, bit A and B will be on, and then they will be off for the next 5 seconds, and C and D will be on, and so on and so forth. So these are the so-called drums that indicate how the bits will be orchestrated. When we come in to write a programming language for PLC, usually it starts with a block diagram, which could be described easily to non-technical personnel involved in the process, or people which are part of the project, but not necessarily IT or software engineers. So we have a terminator here, a connector, process, input, output, decision point, and again, here are the references, and we recommend that the student will move into it. There are also the different mnemonics for writing software. We're not going to get into it. Certain symbols such as AND for this type of connectivity, or for this type of connectivity. There are also not AND, NAND, and not OR, NOR, which are being used with various symbols which help writing a software diagram. Now here we see an example of a program, a PLC program. We have a system over here which includes an output as a motor, output as a light, and output of a buzzer. And we also over here have a switch to operate the motor. We have another switch to sense the obstacle which may interfere with the motor process, and we have another switch to turn on the light. So A starts the motor, B detects obstacle, C turn on the light. And the problem is to design a simple line follow robotic system to start the motor with switch is on and simultaneously switch on the LED. And then the sensor on the motor, if it detects an obstacle, then the motor is switched off, and simultaneously the buzzer is switched on and the LED is off. So that's the simple process. We have here the block diagram that tells us this. We start switch A if is on, if switch C is on, and switch B is off. Then we ask in the question if there is an obstacle. If there is no obstacle, then the motor is started and the LED is on. If it is, then switch B is on and the buzzer is on. And over here are some of the definition of this process. We could also see over here the ladder diagram. If A is closed and there's no obstacle, motor is on, and then if C is closed and no obstacle, then the light is on, and then if there is an obstacle and the motor is off, then the buzzer is on. We have here another example where we have a gate which separates the outside environment with a hole coming into the gate from the outside. We have over here a switch with a key that we can raise the screen or the door. Then we could also bring it down with this push button. We also on the inside have a switch over here to raise the gate, and then another switch to lower the gate. If you want at any time to stop it, we push this S0 button. And then on the safety side, we have a light screen. If anybody crosses it, then the gate will stop. We have limit switches that, just like in robots, when the gate is all the way up, hitting the switch, it will stop. And then when it's coming all the way down, it will stop. And then when the gate is traveling, then the warning lamp is going to be on. So that is the environment that the programmer has to understand. And then the customer will explain the operation, that it must be possible to open the gate from the outside with the key, switch 1 and then to close it with a push button S5, and inside the hole it should be possible to open the gate with a push button S2 and close it with S4, and then additional items, time switch must close the gate automatically if it is open for longer than 20 seconds, and the state of gate in motion are indicated by blinking light. And then we have the safety features of the push button and the photoelectric barrier and the 2 limit switches. So once the programmer understands the process, then there is an element of defining all the elements which are involved on an input, on an output, giving them address in the PLC, making the remarks, and then starting to write the program. The program over here is shown. We're not going to go through the details of that. Simply taken from the example shown before, and then the mnemonics of the program, shorthand expression of the program, and over here is a description of that process. We can practice PLC programming with Allen Bradley RS Logix 500. It's given to us free online. You could download right from this PDF document the RS Logic programming process language and try to experiment with it. Here's an example that we shown earlier in a course. We see here an index table which is being fed with a cobot, a collaborative robot working in tandem with a human operator. Parts are coming in on a conveyor. A sensor senses a part and then gives the PLC an indication that a part is ready for the robot to pick up. The sensor over here checks parts coming into the human operator, then maybe heavy part, that may be light parts that have to be assembled and maybe processed over here with a machine tool. And then we have an index table that transfers the parts from the robot to the human operator into the machining center. Now we define sensor 1 as on when the part on conveyor reaches the robot station. Sensor 2 is on when the part on conveyor 2 reaches the operator. Robot output 1 is on when the robot finishes pick and place. Switch 1 is on when the operator finishes loading. Index O1 on is when the index table completes the process. And then we have robot input 1 on, clearing the robot from the PLC to go ahead and do the pick and place from the conveyor on the index table. Light 1 is on, clearing the operator to pick a part and put on the indexing table. Index 1 is on, is clearing the index table to rotate, and EMO is on, emergency machine off is active, stop all operation. And then we can, once we define that, as we saw earlier, then we could write the process rules, like, for example, if sensor 1 is on and index 1 is on and the EMO is on, therefore, in other words, the part is here, the operator finished, the EMO is not on, and then robot 1 the robot can place a part, and then if sensor 2 is on and index O is on, another index is not rotating, EMO is off, then light 1 can come off, come on, and then the operator is clear to go. When the robot is not working, when the index table is not working, then the PLC indicates with a light to the operator they can place a part. And then when the index table is not running, and the operator is switched that is finished, and the part is here, then the PLC will give the robot command to put the part on a indexing table, and when the robot is finished, the operator is finished, then there will be a certain delay, and then the index table will operate. This is pretty much the process. We see here the flow chart of that process, and then over here we could practice this with the RS Logic 500 online. This is an example over here that we start the cobot assembly process, and over here we check if the emergency system is off. Then we could, if it is on, if it is closed, we stop all operation. If not, then we continue and we check sensor of robot A, sensing incoming part A, if this is closed, and if there is an indication that the index table has completed its task, and if the operation is not stopped because of the EMO, then the PLC will command the robot to pick and place, and so on and so forth. Now, the process that we will be doing with PLC in our lab experiments pretty much combine both the robot controller and the PLC. And what we will do here is we recommend that the students in preparation to the final project and the project 10, where we'll be using I/O boxes, is that the YouTube here will describe how we use the PLC to be tuned for an input from the operator. So here's a block diagram, the flow chart. We can look at it when we start. We have a subroutine which is looping all the time, and then we check in if switch 1 is on. If switch 1 is on, we go on and we do a process. In this particular example is a robot bartender, and we pick a certain bottle and we pour it, and then we place the bottle, and then we go back to the loop, and the loop continues, checking if the switch is on. If not, checks if switch 2 is on. If switch 2 is on, the robot picks a different bottle and goes through the process and goes back to the loop. And then if there is an emergency stop over here, then the robot will sense that and will stop all operation. And if it's not, and none of these switches are on, then the loop will pretty much continue doing this forever until the machine is stopped or one of the switches is being placed. So we will practice this both in the robot barman experiment as well as in a final project. This completes our presentation for process control, and we will do more of it in upcoming lab experiments. Thank you.